I'm Gopal Madabhusi, and the question I was asking was kind of slightly to set up the scene for what I'm going to talk about. So I'm going to focus today on the use of high gravity centrifuge testing. And the real idea of introducing this to you is to talk about how are we going to actually prove that all the technologies you guys are developing actually work. And until we do that, it'll be quite hard for us to sell it to the industry, as it were. So can you see that all right? Sorry for the bad color choice. But obviously, as I was saying, the development of these new smart materials, they have to be tested so that you can promote their widespread use in the industry. Now, there are various modeling techniques that are there to help us achieve this. And in this lecture, I'm going to focus on a particular type of material, so, the soil or nonlinear materials, and give some examples of how complicated the real life problems are and how we are trying to model that using a geotechnical centrifuge. We'll follow up this with hopefully a nice lunch for you guys. And we'll see you at the Schofield Center, where some of the facilities I'm going to talk about now, you can actually touch and feel and see how big these things are. Okay, that's the plan. Okay, generally engineers of today, before you try to design anything, what are the tools that we got? For simple problems, as you would have done in your undergraduation, you would have probably empirical, semi-empirical methods that can be used for design, and some kind of a closed form solutions for the problems. So, for example, if you want to design the foundation of a building, you would go to bearing capacity factors given by Terzaghi, look up the bearing capacity factors for the friction angle, and off you go to design. That works for simple problems. For more complex problems, and this is more and more the case, especially in Europe, is that you rely on finite element analysis, which is great. When you're using the finite element analysis for any problem, the difficulty is always the constitutive model. So if you got simple materials which are elastic, then it's not an issue. We can do it easily. But when you're dealing with complicated materials like soils, the constitutive model can be rather intricate and difficult. And you also need to know how this constitutive model performs under different loading conditions. For example, what will it do when you're applying cyclic loading and so on. So if we know the constitutive model, then of course our FE codes work. But if we don't know the constitutive model, or we are not confident it does the right thing under the particular loading condition, I'm going to focus later on earthquake loading, for example, which is a big issue in Italy, Greece, and elsewhere. Then what do you do? So to answer this question, let's look at the simplest of stress strain behavior of soil. For example, if you take a bit of soil, put it in a shear box and shear it, we know that if I plot the stress versus strain, if I pack the grains tightly, I'll get the dense sand behavior like that, shown by the red line, where you get some peak strength, and then you got some residual strength with increasing shear strain. But if you got loose sand, it'll be continuously shear hardening and follows the green line. Now, this is all great, but if I want to try and test in a laboratory by making, say, a small scale model. So I build myself a reduced scale model of the foundation, apply the loads, and then the behavior I get from the soil will basically, because I'm at very low stress and low strain, I will invoke the stiffness here, which is the tangent to these lines, which is going to be quite high. Which means when I test a model in the laboratory scale, like the nice little tabletop models you're testing for concrete, I will get completely the wrong answer, because the stiffness is so high that my model will predict that any settlement of the foundation is going to be quite small, because the stiffness of the material is very high. And if I use this and design a building like this and construct it, then the stresses are up here somewhere, let's say, and over here, then the stiffness I'm going to get is a much smaller slope, right? Compared to here, I have reduced the slope. So clearly, we cannot be testing in a small scale for materials which have nonlinear behavior like that. It's a very easy way to explain this. So what do? We somehow need to get the stresses and strains to the same level as you will get under the real structure. And this is where centrifuge modeling comes in, and it is the easiest thing to explain, especially before lunch. This is probably schoolboy physics, so it is very easy to understand. All I need is that you to imagine a block, say whose dimensions are L, B, and H, with a mass M. Now, if I ask you what is the pressure this block is going to exert on the ground, you would simply say, well, the weight of it is mg, and it's sitting on an area of LB. So the vertical stress or vertical pressure is going to be mg over LB. Similarly, we can say the strain by definition should be change in length over original length. Now imagine that I scale this down by a factor of n. So the length is now L over n, the breadth is B over n, height is H over n. So all the dimensions I have squashed. All I'm going to do is to change the G from, instead of 1g, which is the normal gravitational level you have, to n times the G. Let's see what happens to the pressure. Now, the mass of this block, because I squashed in all directions, is going to be m over n cubed, obviously. So I'm taking m over n cubed and I'm putting it in a ng. So the vertical pressure is going to be m over n cubed times ng over the reduced length L over n and B over n. Now, miraculously, all the n's cancel out, and I'll get exactly ng over n. So the same vertical pressure will be exerted by this block on the material underneath as that the big one. Similarly, strains also work out perfectly, that you get change in length over original length as you get in the underneath the big block. So what we are saying is, if I can reduce, apply a scale factor on the buildings, the soil layers, and so on, and reduce them by a factor of n, put them in a centrifuge to increase the gravity by a factor of n, then the little model we built is going to behave exactly like a real building. So all I need to do is to increase the gravity now. How do I increase it? Put it in a centrifuge. We all know centrifugal acceleration is r omega squared. So if I can match my mg to r omega squared, then I'm in business, basically. So that's fairly easy to do. So suppose I want a 100G test. So I scale my model by a factor of 100. Imagine I got an earth dam, which is 100 meters high. Clearly, it's much easier for me to build a 1 meter high earth dam, put it in a centrifuge, and spin it at to get the 100G. And if I have my centrifuge is say 4.25 meters, then I only need to spin it at about 145 RPM. These are typically the dimensions of the centrifuge you're going to see later on this afternoon. So far so good. This is all works out nicely. So whatever the big 100-meter dam is going to do, my little meter-high dam is going to do exactly the same thing, allowing for the nonlinear behavior as well. So this is a picture of the centrifuge you're going to see later on. And this is what we call the Turner beam centrifuge. It's a balanced beam, which means whatever model we want to test on one side, we put a counterbalance on the other side. So the moments about the central axis are 0, and the whole thing spins around. Okay, you need to go underneath the ground to see this, but it'll be fun, I promise. And typically these things are rated as how many tons you can carry at what G, and so they're classified as G ton. Our centrifuge has 150 G ton capacity. In other words, it can carry 1 ton up to 150 times the normal gravity. So this is one of the older centrifuges. You can get newer ones. There's bigger ones. Americans always must have bigger ones. The Davis centrifuges their our diameter is their radius, so it's twice as big, literally. Okay, but it's also an old machine and ex-NASA. But you have a much nicer looking ones. Obviously, the French care a lot about the design. You can see this looks quite shiny and beautiful. This is the centrifuge USTA, LCPC it used to be called. And it has a nice gondola. It's very nicely streamlined. The French are always about form over function and the rest of it. So it looks beautiful. And they have a bigger version of this at the US Waterway Experiment Station. This is a really large machine where it can go up to 350 G, carrying 2 tons. So it's a 700 G ton machine. And there is also commercial companies like Takanaka, for example, in Japan, centrifuge modeling is quite big. So almost every construction company has a centrifuge for themselves. This is, I always put this picture because I was responsible in designing and building this in collaboration with IIT Bombay. And this is a homemade, made in India centrifuge. It also works perfectly fine. Okay. Now, the real trick with this modeling technique is that we can see and observe what happens in this small scale model using instrumentation, just like you are doing in your laboratories. Then whatever we're observing, we need to be able to relate that to the real big structure, which we are imagining in our mind, what we normally call the prototype. So to do that, we need to have links between or rules or scaling laws that link the observed behavior in the model to the prototype. For example, we call them scaling laws, but I already explained to you the scaling laws for stress and strain. The whole point is that we derived those and we said that's going to be 1. So whatever stress I have in my model is the same stress will be there at homologous points in the big prototype. We also know that the dimensions have to be scaled down by a factor of n, and the mass by n cubed, and so on, and acceleration by a factor of n. So if I put them in a list, these are all the scaling laws you already know. And it took me less than 10 minutes to explain that. So it's really easy to understand this. What about other things that we don't know? For example, we don't know about force. We can derive them quite easily. All we need is, again, as I said, school level physics. So we know, for example, I want to find out the scaling law for force. The force, obviously, we are not too far from Trinity College where Newton was there. We all know F equals to ma, right? So the forces in the big prototype structure is say mass times acceleration. In the model, we know the mass is going to be m over n cubed, and the acceleration is going to be n times large, right? So if I plug those in, I can relate the force in the model and the prototype, and the scaling law for force is 1 over m squared. So this is quite useful because we can, when we are doing this test in a centrifuge, the forces work to our advantage. For example, in your prototype structure, let's say you want to apply something like 200 tons. Typically, these kind of loads you need to require. Say I want to test a pile foundation and under lateral loading. I need a big actuator to push the pile horizontally, say with up to a force of 200 tons. That's typically 2 meganewtons in proper SI units. So that's a big force. Now, suppose I want to do the same thing in a centrifuge mode with a smaller pile spinning around at say 100 G. Then the force I require is, because we already know the scaling law for force is 1 over n squared, 2 times 10 to the power of 6 newtons over 100 square. I only need 200 newtons of force to apply. 200 newtons of force I can live with. 2 meganewtons is a big, expensive thing to move to the, if you want to do the field test, it will cost you upwards of a couple of £100,000. And if I want to build an actuator that can apply a 200 Newton force, that's going to be fairly small and easily manageable. It's after all, 200 Newtons is about 20 kilograms of force. Okay, what about energy? Energy is based, again by definition, is work done or force times distance. We already know the force is F/m squared, and distances we know we have to scale them by a factor of n. So instead of the energy scales as 1/n cubed. So for any parameter you want, we can easily derive the scaling laws and be able to link what we see in the model to the prototype. So energy scales as 1/n cubed. This is also quite useful. You say if you want to test things where energy is a key component, explosions, earthquakes, those kind of things, where there is a lot of energy that is required. Suppose I want to anticipate an event where I'm going to explode something that will yield 1 terajoules of energy, terajoules of energy. So that's 1 times 10 to the power 12 joules. So because the energy scaling is n cubed in a 100G test, that is equivalent to about 1,000 kilojoules. 1,000 kilojoules is almost like the detonator cap people use in rock to explode dynamite stakes. You have a detonator cap, and that cap has about less than half a gram of TNT. So if I can use half a gram of TNT in a centrifuge test, I can basically model something that is massive in the field. So yeah, in many cases, this comes in quite handy without actually requiring to draw up an entire block of buildings or anything like that. Okay, so those are the easy ones. Another quite interesting thing, and people, earlier speaker was talking about this diffusion of, say, ions and so on. Especially where we are dealing with clayey soils, consolidation is a big issue in soil mechanics, generally geotechnical engineering. The problem with consolidation is clay has very low permeability. So if you come and construct, say, your embankment or a road on clay, it all feels good because all the weight is taken by the water between the soil particles. And as you walk off the construction site, slowly over maybe next 2, 3, 4 years, the water starts to move out and the whole soil layer starts to settle. So this may take 10 years. And that's a problem. But what we know about it is that the process of consolidation is basically a diffusion equation. And we can write this in a 3-dimensional W/dt is CV del square U format. And that conforms and where CV basically is the one thing which we require from the soil, which is the coefficient of consolidation. Now, if I want to capture this in a centrifuge, what I can imagine is the degree of consolidation is controlled by what is called the time factor, which relies on the coefficient of consolidation, which is basically the property of the clay, and the time it takes to consolidate, and the distance. Well, we know from soil mechanics, this is the important set of dimension group. So if I use this and say that this TV must be the same in the model and prototype, then I can say how long will I take in the centrifuge to reach the same level of consolidation as I would in the field. So I can pick that equation. So I'll write it for prototype and the model just with the different suffixes. And what we want is the left-hand side on both these equations must be equal to 1. Then we can compare one to the other. Now, then I can write this as such, divide one with the other, let's say, and that's left-hand side becomes 1. And if I use the same clay as I have in the field in my centrifuge model, then I expect the property coefficient of consolidation to be the same. So the ratio, this ratio also becomes 1. So I'm only left with those things. The time to consolidate in the model versus over time to consolidate in the prototype over the drainage distances squared. Now, if I now try to work out the ratio of the time in the model to time in the prototype for a consolidation event, then it becomes d model or d prototype squared. And we know the distance is scale as factor of n. So you plug that in and we got a 1 over n squared. And this is quite useful because if, for example, I have a 10-meter thick submarine clay deposit on which I'm trying to construct, especially on the offshore Mumbai, it probably takes about 10 years to get to something like 95% consolidation. So if I construct something now, I will only know how much is going to settle after 10 years from now. Now, suppose I use the scaling law in a 100G test again and work out how long will it take to do it in the centrifuge. So I just put 10 years, 365 days, 24 hours, 60 minutes, 60 seconds, over 100 squared. So that must be how many seconds it should take in the centrifuge model. So if we do that and work out the number, that turns out to be about 9 hours in a centrifuge at 100. This is very manageable because I can run the centrifuge for 10 hours, no problem, which means I can tell you how much the foundation is, the embankment is going to settle 10 years from now by running the centrifuge for about 9 hours. So you won't disagree with me if I say we have actually invented a time machine as far as consolidation is concerned. It can't move people from one time to the other, but certainly it can predict what's going to happen in about 10 years' time. Okay? So these are the kind of things we can do with the, even for complex behavior like soils where we don't have real understanding of how things work when it comes to really complex structures. So what are the advantages? The advantages are that you are creating the correct prototype stress and strain in the centrifuge model. That is its biggest strength. And therefore, the soil will mobilize the right stiffness and true behavior of the material is mobilized. Now, the other point is that even when we have new materials, like the materials you guys are developing, that's not a problem. We don't need to spend a lot of testing on the understanding the constitutive behavior. We just need enough of that material to put it in the centrifuge. And even for unknown material, we know we will capture the right stress path and the right behavior at the prototype scale. The third point is that, and this is probably its greatest strength, is the true failure mechanism is always mobilized in the centrifuge. I'll show some examples shortly where some of these will become very clear. The other thing is because we are making physical models, we are always dealing with three-dimensional behavior. Even now, if you want to run, say, for example, for a pile group, if you want to look at the three-dimensional behavior, the 3D finite element analysis is quite cumbersome and can take quite an expert to make sense out of it. Whereas in the centrifuge, our PhD students just build the model, put it in the centrifuge, spin it, it does what it wants to do, you just observe. So the three-dimensionality is not an issue. Okay, there are other fringe benefits, as it were, which is the soil structure interaction is automatically accounted for, where you've got buildings and soil working together. These things are automatically accounted for. Long-term events like the consolidation, we're able to capture nicely. And this is, I picked consolidation as one process, but all diffusion processes we can capture wherever there is a coupled diffusion problem. For example, if I have clay with contamination inside it, then you got two sets of equations effectively to solve. One is that the clay is already consolidating. On top of that, you also have the diffusion of the contaminant. Those kind of problems can become quite complicated mathematically, whereas in the centrifuge, you can just do them in one go, and it does what it wants to do. You use the instrumentation to observe what you want to, what is of interest to you. And it's relatively cheap. What you see today, where you may feel that, oh, the centrifuge testing is very expensive, But if you compare to the quality of information you're getting, it's actually quite cheap compared to any field test you can do. Because it involves a small scale model, once you have the centrifuge facilities, it's not all that expensive to make the centrifuge test. Also, it is possible to test where real scale events are impossible to model. I work predominantly in earthquake engineering. I cannot wish an earthquake on anybody. And even if I wish, it's not going to happen when I want it to happen. So for studying problems like that, same with the blast events, you can use centrifuge tests to create these unexpected extreme loads onto the structure and see if it works, cyclic loads. Okay, now I come to 3 applications that probably will finish a little bit early so that you can have a lunch early, but let's see how it goes. And these are, I picked the ones we are working on most recently, but I have a ton of them in this computer. If you are interested in any other problem, I'm sure I can find some other applications. One of the interesting things is that with the advent of new materials, with the corrosion and so on, the use of steel sheet piles are on the rise, especially for creating harbor facilities. And this is why the ArcelorMittal are interested in this, because they want to push the steel sheet pile walling as much as they can. That's their job. But there are a few issues, and there have been some failures in the past, especially in Japan. Typically, an anchored steel sheet pile wall would look something like this, where you got your waterfront. We have something similar on the Cam River as well. If you walk along, you can see it, where you have a steel sheet pile wall and you got an anchor going through, and at the back you got a plate on which you attach the anchor to. And normally the water level is somewhere like that. The problem is that when earthquakes happen, it seems that this ground behind can move or liquefy even, and you get failures like this. So there are 2 types of failures largely that can happen. One is that just the soil in front of the anchor fails, and the anchor simply slides, allowing the wall to rotate. Now that's what we call the local failure. Or else you can have the global failure, which is much preferable, and because you've got a lot of resistance for this to happen, where like that, what you're seeing there, the whole unit shifts. And this typically happens when the ground here liquefies. But that's a different story. But at least you will agree with me that these are complex problems. You've got lots of bits to it. So we can model that in the centrifuge. You've seen the centrifuge already, but we also have this other governance that go with it, which is a transparent side box and a camera that looks into it. And one of the tricks we have developed recently is to look at these from the side and observe where literally each grain of sand can go. So we have what's called a Geopivian software, which can track where in sub-pixel space, how much each grain is moving, so that we know exactly what the strains are. So this is a fast camera, which takes about 1,000 frames a second and fairly high resolution for the job it does. But imagine all this has to happen while the thing is going around at about 150, 200 miles an hour. So the trick is to make them work when they're flying around. So to focus on the problem I explained earlier, we have ourselves a model where we got about 8-meter high wall embedded 2 meters, so total 10 meters with an anchor at 17 meters behind. So these are obviously big dimensions and prototype dimensions. To compare that, we have a shorter one where we attach the anchor at the right location, a third below, and it's slightly inclined there. The models look something like this, looking from the camera I've shown you in the previous slide. So you're seeing side on to the model. Okay, so there are lots of instruments, and we fire lots of earthquakes from varying strength from 0. Quite small earthquake like magnitude probably 3.5 or 4 to 0.3 G is probably magnitude 7.5. So these are we got a range of earthquakes we can apply to this thing, and lots of instruments to monitor what's going on in terms of accelerations, bending moments in the wall, and so on. Okay, the first thing is we're keeping the input motion fairly simple at about a fairly strong earthquake, 0.5 G, 0.4 G in both cases, and we're looking at what the acceleration at that level is. And we can compare directly both. We're getting slightly bigger acceleration for the shorter anchor wall compared to the longer anchor wall. Then we can see what's going on in the wall itself, how the accelerations are, and also the forces that are being generated within the anchors as well. So you are getting about 100 kilonewtons in this case, and a bit smaller, but some with residual value there. And that becomes clear a little later. And we can, of course, look at the bending moments and see that the important thing is what are the magnitudes. Obviously, the shorter wall has bigger bending moments compared to the longer anchor wall. And you can see that the magnitudes are, the interesting thing for me is that earthquake after earthquake, we're applying 4 or 5 earthquakes, you can see the bending moments increase and stay. So the residual bending moment is always there and keeps increasing after every earthquake. So the wall kind of remembers that it has seen an earthquake and therefore it must carry this extra bending moment. So when you're designing these things, you need to design to withstand obviously for the worst case situations. If you look at from the camera itself, you look at where the walls have gone. The front wall, in this case, after each earthquake is moving horizontally and also rotating. And we can also track what the back wall is doing, the anchor wall is doing at the back. And you can see that thing is rotating. That's because we attached it at the top third position. Whereas in the shorter case, it's also moving, but it's moving more or less horizontally, but by a long distance. These are in centimeters. And the whole wall rotates. So we can see the failures quite well, and we can also get the displacements of these points directly from the PIV. The most important thing is this slide, where I'm plotting the contours of the displacements. So where is the soil actually going, and where is it moving most? Anybody will tell you that it will move highest just at the top of the wall, because the wall wants to move further, the soil can follow it and fall into the gap. But you can see the difference in the 2 tests we have done. In the first case, the highest displacements are happening just behind the wall, anchor wall, and behind the main wall. Whereas for the shorter case, the whole thing, we got this whole thing moving. Those are the equivalent shear strengths. Ignore those for now. So if this is what's going on, we can clearly see that that is what we call the local failure mechanism at the start, and this is the global mechanism. So we are able to capture exactly what is happening in the field using the centrifuge test. Okay, so that's one example. So just a few comments to summarize, which is the deformation mechanisms behind the anchor walls are captured very well, and basically the deformation changes depending on how long the anchor length is. Now the application for you is that if you are going to say you use new materials behind to do the backfill, say you want to strengthen the soil behind, how is it going to behave even under an earthquake loading? You can do these kind of tests, and you don't need to produce thousands and thousands of cubic meters of material to do a field test, whereas you can, if you give us something like say 20-30 kilograms, that should be enough material for us to do tests like this. Okay, so that's one application. As next, I can stop, by the way, at any point. If you're feeling too hungry, put your hand up, I'll stop there. I can, as I said, I got lots of applications, but depends on your interest. This is another complex case where we have structures now being built quite close to retaining walls. And you'll meet Gloria later on, and you can talk to her more about it. But this is the problem we are facing, especially in big cities like London, Rome, and so on, where you got buildings and you want to create underground space just next to it. So you create these kind of retaining walls to hold the building while you're excavating and doing whatever you're doing here. Now, what happens if you get an earthquake at that time? Obviously the building is there behind the retaining wall. We just saw the retaining wall itself before. Now we got this extra problem of the building. Same thing is also true for ports and harbors, where you got crane structures running along the waterfront. So I'm introducing another one, which is the numerical modeling here. So we can do these analysis using some specialist finite element code called Sine, which we use, but you could do it in Flaxis or Clack or Furvid, where you can create meshes like this, where that is just the retaining wall, and this is the retaining wall with a structure. And we can run these analyses, and basically we created that mesh to match exactly our centrifuge model, which we also did the tests on. So this is the model with the structure behind, and you can see the retaining wall. Again, the same imaging techniques are used. One of the advantages of doing numerical modeling is that you got a good idea about the stresses. So if I apply no earthquake just under static conditions, we can get the horizontal earth pressures. Clearly, you get big pressure bulge, passive pressure bulge in front of the toe of the wall, as you'd expect. Now, when I apply the same thing with the structure, you can see that bulb in front is much, much larger in front of the wall, because the structure is trying to push on the wall, and the wall has to kick more at the base, so you get a bigger pressure bulb at the base. Fairly straightforward. What about the bending moments? Again, just from numerical modeling, we can say what was the case of the bending moment in the wall when there is no structure, which is the blue line, and when we put the structure, we get much bigger bending moments. And the same thing is also true for the earth pressures. And we can put active and passive limits on that to see how much earth pressure is mobilized. Okay. So when we apply the earthquake, we can also see what's going on cycle by cycle. If I take an early cycle like this, and you can see at different points along the acceleration what the bending moments are, and you can see that they are increasing. If I take the same analysis, but look at a later cycle towards the end of the earthquake, you can see my bending moments have increased significantly compared to earlier in the same earthquake. Now, the magnitude of the shaking is almost the same for both, but you can see because of the number of cycles, this thing got a lot worse. And this is something which designers must be careful about. This is the most interesting thing of in this problem is what's happening to the displacements behind the wall. You would expect that the structure would make things a lot worse, and it does in terms of the bending moments. But if you look at just the wall itself, as before, we get big displacements behind the wall. Red is obviously large. And when I put the foundation, it makes it quite worse under the right-hand side of the footing. But on the left-hand side, it's much smaller. Not only that, it's stopping these deformations going all the way back to around distance. So it seems by putting the structure, we made the problem worse right underneath the right footing, but under the left footing, we improved it. This may not do the structure any good, but what it tells us is there's a big interaction going on between the structure and the kind of deformations you get. Now, imagine you're going to use your self-healing soil improvement techniques. Now, what's important then is that you need to improve this a lot more than that. And you don't need to keep improving the whole backfill. So you can see how the application of even problems like this can be used with the new technologies. And not only that, you can then say, we tested it properly and it does work. And that gives confidence for the industry to go and use it with the hope that when the earthquake comes, their building is going to stand up. And that's quite important. Exactly the same thing. Of course, that's all numerical analysis. As I said, we need to know the constitutive model correctly. If you do the same thing with the experiments and we get similar results, then you've done the same problem in two completely different ways. And when they match, you feel good about yourself. So that's without structure and with structure, and you can see that we can get the bending moments. That's about all I wanted to say. But also we can look at the rotation of the building and how much displacements you're getting in the wall as well. This stuff is published. You can have a look if you're interested. So the presence of the structure on the backfill side of the retaining wall will affect both the static and dynamic bending moments that you can expect. But the displacement field in the backfill is completely altered by the foundations of the structure. And that is the lesson we learned from this particular work. About 10 minutes, I think, probably. You're not too hungry? Okay, in that case, I'll carry on. This is another massive problem that is coming our way, which is the offshore wind. Obviously, there's been COP26 and everybody wants green energy, and we're all pushing to create more and more energy from offshore wind. Now, typically, these offshore foundations are placed on a monopile. I'll explain what that is in a second. But the big problem is the same when this technology evolved, say in Germany, Denmark, and in the offshore UK, then we are not so seismically active. So we were happy to make these big steel piles, dry them, and put the offshore foundation. But now the same companies are expanding to Southeast Asia, Japan, South Korea, and also the off coast of California, which are all highly seismic. So we're all scratching our heads on deciding what's going to happen when big earthquakes happen, because this is not one wind turbine you're going to talk about. In a wind farm, there are about typically between 1,000 and 1,500 wind turbines to make enough energy. So if you get a moderate earthquake and all of them keel over, then obviously you're at a total loss. You can't do anything with this. So we are looking at that in some detail, and you will see a couple of projects this afternoon about that as well. So what are monopiles? Monopiles are fairly large tubes of steel. This is the size of a person, fairly tall person, and you can see that's the diameter. So typically we're talking about between 6 and 8 meter diameter tubes, and that go about 30, 40 meters into the ground. So these are very, very big structures, big foundations. And just to give you an example, this is a problem we're going to look at. So we try to drive them into the subsea. So the water level is there, and we're considering, say, something like 10, 15 meters of water there. And you got some loose soil on the top, and you try to drive them into dense sand, obviously, because you have to carry the load. And typically, you're expecting something like 3 meganewtons horizontally and maybe 4 meganewtons vertically. The moment load is the big problem in these things. And so the problem we are trying to address is what happens if you have some kind of an earthquake loading coming here, and this stuff actually liquefies. Is this still going to stand up or not? Is the big issue. Not only standing up, the people who make these turbines are quite demanding mechanical engineers. So they insist that the rotation at the seabed level should not be more than half a degree. They have good reason to say this, because if I allow half a degree of rotation of this pole here, the movement at the top, which is about 100 meters above in the air, is going to be huge, isn't it? If I rotate something by half a degree here, and I have a very long pole, the amount of distance that has to go is going to be huge. So they are a bit worried that if you go so far away with these generators and the blades hanging on at the top, you get quite a lot of gyroscopic forces if they go inclined. So they limit the rotation to less than half a degree. Now, is this achievable when you have this kind of extreme earthquake loads? So what we were looking at is, first of all, what is the lateral capacity of these piles before and after the earthquake? And nobody in the world has any idea of this at all. So we kind of got in there and did some tests, and I'll talk about them in a second. Also, by using sine sweep motion, we can identify the natural frequency where Fn, which is the most important frequency for the offshore wind turbine system. And then we apply strong earthquakes at Fn, 2Fn, and 3Fn. And we wanted to measure the dynamic bending moments. This bit did not work very well, I'll be honest with you. And we have to improve on that. But also we are interested in looking at what is the dynamic response of the structure. So our model is very simple. So we lumped all our mass at the top, and we got the piles. And what we have is a system of actuators where we got two identical piles and two identical actuators, which can push these horizontally, and we can measure both the displacement and the load. I'll come and show you what we got later on, but that is the system. We also have accelerometers everywhere to measure the accelerations. So this thing looks, when you put it on a centrifuge, looks something like this. You can see these actuators are quite small. Remember, at the beginning, I said to you, in the centrifuge, the big advantage is we can apply quite a large prototype force by using fairly small actuators. This is all the actuator we have in the centrifuge. Whereas if I want to apply the same load in a prototype, on a prototype pile, I can't even do it. I need such big actuators. I can't react that against anything else, because these things are hanging in a boat. And if I try to push the pile, of course, the boat will go the other way. So you have nothing to react against. So it is quite a big advantage in this case. And this is a close-up view. My student obviously liked this picture a lot. And you can see that this is the servo-hydraulic shaker, which I'll show you when you come to the other side. Also, we are able to characterize our material quite well. And we have measured here the shear wave velocity with depth. And we can see the loose layer has smaller shear wave velocity, and the dense layer below, we are having larger shear wave velocities and therefore shear modulus. And you can compare these with existing literature, for example, Stupak and Bolton or Hardin and Greenwich. So those look reasonable. Now, first thing we did was to apply a sine sweep motion at the bedrock level and see what's happening in the sand. Obviously, not much is happening in the sand because it just does the same thing. Here, the input motion is changing frequencies as we go from left to right, increasing frequencies. However, when it comes to shallow sands, you can see the size of these things is getting bigger. So the accelerations as they come to through the loose soil are getting bigger. Now that's one interesting thing. But even compared to that, if you look at what the top of the pile is doing, the top of the tower is doing, those accelerations are massive. I'm only putting this size input, and you can see the size of the output I'm getting. So if I put a tiny acceleration at the bottom, the top is accelerating quite a lot by a factor of 4 or more, larger. So you can do this by doing what typically we plot these spectral accelerations. That's not important. All that's important is that at the natural frequency, if this is the input I'm putting, I'm getting an output which is massive, which is a problem if you're the owner of these kind of facilities. However, if I put more realistic motions like the Kobe earthquake motion, the tower doesn't do anything. So it likes certain frequencies, and if the earthquake has that input motion, it amplifies significantly, but for other types of motion, it doesn't do anything. So it's important for us to know what input motion we are putting. In this case, where I put exactly the natural frequency of the structure and apply an earthquake, you can see I'm getting more than 0.5, 0.6 G at the top. What about the bending moments? The bending moments, I said, did not work everywhere, but at least we got some devices which worked. And you can see there are 3 different tests And this is the dry model, this is the saturated ones, and you can see you get quite a lot of bending. When I do the same thing at twice the natural frequency, you can see nothing happens. And similarly, when we did the 3M, also it did not do very much. The other thing we tried was, initially I said that we had two sets of monopiles, which we are pushing before and after the earthquake. And as we are pushing, we can see what happens to the bending moments. So we can see the shape of the bending moment as we apply larger and larger displacement. And once we got up to about, say, 13% of the diameter, you're mobilizing something like 30 meganewtons, meganewton meters of bending moment. But what's interesting is this stiffness. If I take a dry sand sample, because a lot of people who design these things imagine that these things can be fully drained, and if you look at the PISA project and other things that Imperial have done, they imagine it to be drained material. Of course, soil drained and undrained makes a big difference. But what we did was, if I pushed the pile in a dry sand, you get the initial stiffness before the earthquake. Pre-earthquake one is this line here, and that is stiffer compared to the post-earthquake. So post-earthquake, the stiffness is dropped in the dry case. But if I do the same thing in the saturated case, you can see the post-earthquake stiffness is higher than the pre-earthquake case. Now, this kind of information is extremely important when you're designing these things. Given that these things are actually sitting below the sea, of course, the soil is fully saturated. Therefore, we need not worry so much about the drop in stiffness in the post-seismic period. What our tests are showing is you should only worry about that if you've got dry soil, but if you have saturated soil, your stiffness is in fact going to increase. Now, that could be of some comfort for the designers so that they don't worry about the wrong kinds of things. Okay, that's, I think, almost on spot on time. So some very interesting results are coming, but of course, this is a very early stage. We are writing more papers and analyzing this data more carefully. But we seem to, we are able to find the dynamic response for very large earthquake frequency range. And we can also see what happens when your earthquakes hit exactly at the natural frequency of the system. And the changes in initial stiffness are very, very interesting. And this dynamic loading, which largely was ignored by the offshore industry, is now coming back to show how important it is to consider those things, especially where you expect seismic loading. And of course, there's soil liquefaction to worry about. So I hope I have proved to you in the last hour, A, centrifuge modeling is fun, easy to understand, and can provide lots of interesting ways, not just for geotechnical people, but also structures and where people are coming up with new materials whose behavior we do not know, mechanical behavior we do not know. And for scaling things up from tabletop experiments to before you spend millions of dollars doing field studies, there is a nice intermediate step in between where for only 10% or even 5% of the cost of a field trial, you can do some centrifuge tests nicely and really establish what exactly is going on with the material. So I've shown this with different soil-6 interaction problems, anchored sheet pile walls, retaining walls with buildings behind them, and of course monopiles for offshore wind. As I said, I just picked these because these are the most recent ones we have been working on with students around, and some of these things you can see this afternoon, and they'll show you how their structure looks like out there. They'll probably have some posters and things, and you can talk to them. Okay, if you have any questions, I'm very happy to answer. Thank you. Yep.
We have a question from the chat. How does heat transfer? What is the scaling law for heat transfer and how is heat transfer considered in centrifuge models?
Okay, that's a very interesting question. We actually got a collaborative project we're doing currently with people in, I think they're now calling themselves Gustav University. I think it's the Gustav Eiffel University, but it used to be something else before, where we're looking at geothermal piles and where you have interaction between, say, piles which are getting hot and cold because of geothermal applications, and how they affect the performance of the building. So the mechanical behavior of these piles is also important at the same time. So this is the kind of thing I was talking about, where you have double, two sets of equation to contend with. One is the heat equation in this case, and the usual consolidation equation from soil mechanics. Centrifuges play a big role. Equally, where if I just want to look at heat transfer, then I can do that at a small scale, because that doesn't really need any, there's no benefit in doing this increased gravity test. But where you have real structural elements like the piles, we need the centrifuge. Also, where you have combined effects, like, for example, seepage, consolidation, and heat all happening, which is the real field case, then obviously we need to go to the centrifuge to do that. Okay, the scaling law works pretty much like how the scaling law works for the consolidation I explained earlier.
Thank you.
Okay. Yeah, please.
For sample scaling, but it's obvious for structures for data scaling, but about our soil, I mean the length of the soil, and this, because soil is elastic in top space, and especially for uplifting or rocking, you have radiation gap. How much should be the size of the samples to reach to capture those kind of things?
Absolutely. Very good question. The damping is one of the important things, and a part of, I guess, going back to Abir and my time, PhD, long time ago, one of the early things we worried about is the amount of radiation damp. And what we found was that when you're dealing with soil, the material damping is the biggest proportion of radiation damping and any structural damping. Structural damping is of the order of about less than 1% normally for steel structures, about 5% for concrete structures. The amount of damping in soil is about anywhere between 10 to 20%. So the structural damping just is drowned by it. The radiation damping, I did some calculations early on, which show that the radiation damping you get is about of the order of about half to 0.75%. Okay, so yes, it is present. We try to make the boxes as big as we can to include as much material as we can, but there will be boundaries. One of the things we do is to minimize the boundary effects. We have some special containers, which you will see, which will, when you apply shaking, the boundaries of the box are not rigid. They try to deform, and we design them to either deform without any stiffness so that the soil can do whatever it wants to do, like a laminar box, or we can have the boundaries match exactly the stiffness of the soil. So that if the soil wants to go into, say, the first mode of vibration, the walls also do the same. So you will, yeah, those have been considered very carefully, and we feel we got a good handle on it. So the errors due to that are fairly small. Does it answer your question? Okay. Any other question? Okay, you guys must be ready for your lunch. Thank you very much.